Okay, let's dive right into this explainer. We're going to take a stark, uncompromising look at the concrete data hindering our global move away from fossil fuels. For years, the narrative surrounding the global energy transition has been bathed in this relentless optimism. But today, we're going to set aside the marketing, the ideology, and the hopeful projections. We are going to look strictly at the physical, geographic, and economic reality of what it actually takes to power modern human civilization. Between 2015 and 2024, the world poured a staggering $12.5 trillion into renewable energy production. Just sit with that number for a second. It's massive. In fact, it surpasses the $11.8 trillion invested in fossil fuels during that exact same time frame. If we're looking strictly at the financial ledgers, the transition appears to be well underway. But here's the brutal reality of that massive investment. Despite deploying $12.5 trillion, the fossil fuel share of our total global energy supply, it's dropped by a mere 4% since 1990. We went from an 85% reliance on fossil fuels down to 81% in 2023. Over 3 decades of effort and a literal mountain of capital has barely moved the needle. To understand why, we need to strip away the toxic optimism and look at 5 immovable hurdles of global industrialization: the trillion-dollar paradox, density and capacity limits, geography, grid, and rent, the high-heat industrial hurdle, and finally, the cost of modernity. Let's start with hurdle number 1, the trillion-dollar paradox, looking at investment versus actual results. Back in 1857, Karl Marx wrote that the concrete is concrete because it's a synthesis of many determinations. Basically, material reality matters over ideology. Energy production is no exception. It isn't just about environmental goals or financial capital. It's a complex synthesis of physical laws, chemistry, geography, and raw human demand. We have to analyze exactly how energy is actually produced and consumed. Let's look at the data to build a clinical picture of our current reality. Check out the primary energy supplies between 1990 and 2023. Coal, oil, gas, they haven't vanished. In absolute terms, they've surged massively. Coal supply is up over 86%, petroleum is up over 42%, and natural gas, it's more than doubled, up nearly 115%. The reality is the world is just consuming vastly more energy overall, and fossil fuels are still bearing the overwhelming brunt of that load. Moving on to hurdle number 2, density and capacity limits. We're talking about the immutable laws of physics. This brilliantly illustrates the sheer geographic inefficiency of renewables when you compare them to the incredible energy density of thermal and nuclear plants. We measure energy density in megawatts per square kilometer. Nuclear power can generate thousands of megawatts in a single square kilometer. Fossil fuels generate hundreds. But look at photovoltaic solar. That drops to between 20 and 60 megawatts per square kilometer. Wind is even lower, just 2 to 10 megawatts. So to replace a single coal plant, you don't just need money, you need an exponentially larger footprint of physical space. And we also have to account for reliability. Let's establish a clinical definition for efficiency here, the capacity factor. Because, look, a megawatt of capacity on paper means absolutely nothing if the sun isn't shining or the wind isn't blowing. The capacity factor simply measures what a plant actually produces over time versus what it theoretically could produce if it ran flawlessly 24/7. Now, what's really interesting here is the stark contrast in real-world performance. Nuclear power operates at an incredibly high 76% efficiency. Thermal plants, like coal and gas, sit around 44%. But look down at the bottom. Wind operates at just 27% capacity, and solar languishes at a mere 13%. Think about what that means. You literally have to overbuild solar capacity by roughly 6 times just to match the reliable, continuous output of a single nuclear facility. That brings us to hurdle number 3, geography, grid, and rent, the spatial paradox. Because renewables require so much physical space, they force a brutal geographic trade-off. On one hand, you have places like the Mongolian deserts. The land rent there is virtually zero, perfect for vast solar and wind farms, right? But they're thousands of kilometers away from the actual consumption centers in China. The cost and the energy loss of integrating that into a grid over those huge distances is astronomical. On the other hand, you have land near populations like the Barolo vineyards in Italy. This solves the grid problem, sure, but land there costs upwards of 2.5 million euros per hectare. Solar parks simply cannot financially compete with the revenue of prime real estate or agriculture. Cheap land is too far away, and nearby land is just too valuable. Thermal and nuclear plants bypass this entirely. They can be built compactly right next to the cities that actually need them. Next is hurdle number 4, the high-heat industrial hurdle.
We have to confront raw industrial chemistry.
You see, the majority of fossil fuels are actually consumed directly through combustion to generate thermal energy, not electricity. A household refrigerator can easily run on wind power, sure, but a glass furnace? That requires the direct, intense combustion of natural gas to reach 1700 degrees Celsius. Steel blast furnaces need over 1500 degrees. Cement needs 1450. Petrochemicals require over 1000 degrees. While there are experimental technologies out there, like green hydrogen, they are incredibly costly, present massive technical challenges, and are realistically decades away from operating at a global scale. Today, these foundational materials simply cannot be forged by wind or solar electricity. And here is a cold, hard fact. High-temperature industrial processes are continuous flow. They operate 24 hours a day, 7 days a week. You cannot just pause a 1500-degree blast furnace because a cloud blocked the sun or the wind died down. These foundational industries run continuously, and they fundamentally cannot rely on the intermittency of renewable weather patterns. Finally, we arrive at hurdle number 5, the cost of modernity, the undeniable reality of human aspiration. The scale of human aspiration on this planet is undeniable. The cement, steel, and copper in the buildings you live and work in, that's the backbone of industrialization. They're required for urbanization, transport networks, basic goods. The desire for hospitals, air conditioning, modern infrastructure, that's not a luxury. It is a structural demand of billions of human beings. There are 1.5 billion people in Africa, 1.5 billion in India, and 1.4 billion in China. They legitimately aspire to the living standards seen in Europe and North America. And meeting that massive demand requires energy-intensive heavy industry. Because of this relentless demographic and economic pressure, our global electricity generation has skyrocketed. Just look at the absolute numbers from 1990 to 2023. Despite the trillions of dollars spent on green initiatives, the sheer volume of coal burned for electricity has grown by nearly 140%. Natural gas for electricity has surged an incredible 280%. The basic industries essential for developing the world are still completely tethered to fossil fuels, and that demand is only growing. Which leaves us with a heavy, unsettling reality check. We've poured trillions of dollars into a transition that physically and structurally is colliding at full speed with the hard limits of density, geography, and industrial chemistry. Can we realistically reconcile the legitimate aspirations of over 4.4 billion people in emerging markets with the severe physical limitations of current renewable technology? The concrete data suggests we have a very long, very difficult road ahead. Thank you for joining me for this explainer. I'll leave you to grapple with that brutal equation.